Hey everyone, hope you're doing well. Let's begin talking about today's session, and that is the next part of the series that we started. And today we'll cover CAP and PAC ELC theorem. So, like, what are they, and how it is important in system design? So we'll understand some of those trade-offs as well. Okay, so here is the agenda typically that we'll be covering today. We'll talk about a quick introduction about distributed system, then we'll talk about CAP theorems, then how this PAC-ELC theorem is extending that, and in practical applications, how some of these theorems are playing important role. Okay, so let's talk about quickly what is distributed systems looks like. What exactly it means when we say distributed systems. Uh, so basically, distributed system, when we say it's about when systems are distributed into different geographies, of course, with the network connections that we all know. And after this cloud thing came in, maybe few decades back, it became even more prominent. Distributed systems really kind of flying high because cloud is making that uh, easier, right? Sharing different application data across the globe is really easy now than ever. So this system is really kind of picked up right from that. So this supports sharing of data, state, and network. How different nodes are getting kind of picked up when something is downtime and things like that. So all that is really kind of playing a role in making distributed systems really important. And here is a fact, right, that any global applications is a distributed application because some of data of it distributed across different geography. Even sometimes application is replicated to make it faster access. So pretty much all complex applications, global applications are distributed application. Okay. Now let's understand how this CAP theorem is playing its role in the distributed system. So we'll understand that. So CAP theorem is kind of invented sometime in 2000 by Eric. And what essentially is saying is that basically CAP stands for consistency, availability, and partition tolerance. So what it's saying that in a distributed system, right, in a network partition or environment, you can't have all three at the same time. You got to pick two out of three, right? And you know, and when we start talk about distributed system, we can't afford to not have partition tolerance. We have to have that, right? Because this is essential for distributed system. So what is simply saying is that you got to pick between consistency and availability, right? So you can't have all three at the same time. You have to have some compromise, right? For example, we keep talking about read heavy system, write heavy systems, right? So you got to have a priority that the system is read heavy or write heavy. Accordingly, you pick the different database systems or different design. Like that, we are saying here is that, hey, you can't have both actually. For most part, you got to pick either consistency is really important for you, or you availability is more important. We're not saying that application will not be consistent at all. No, we are not saying that. It will be eventual consistent even the prioritize availability. But we're talking about here is that what is more important for you? Is it a transaction-based system? Of course, it can't compromise on consistency, right? If it is a system which it's okay to have eventual consistency, it's not like immediately every second all the nodes should have the same data, may not be a key priority for application like social media, all that, right? So it's okay to have prioritize availability over a strong consistency. So like that, you got to make a choice. Okay, so that's what essentially is a CAP theorem we talk about, right? So you got to pick either a consistency or partition or availability, and partition tolerance has to have all the time. So basically, we are saying CP or AP system you got to pick. Okay, let's move to understand more. I think I did touch upon what these means, right? Consistency, like all nodes see the same data. You may have read replicas in current systems, a lot many, but so basically we're saying that all of them should have the same data. Availability is about that system is available, means it's okay to have eventual consistency at times, but availability is really important. It should not go down, right? Or if it is going down, it should be very minimal. uh, for 24 operation is really essential. For example, e-commerce. It could be maybe sometime even social media, right? So responsiveness is really important. It's okay to take few seconds for eventual consistency. Of course, partition tolerance is a key, and it can't be compromised for any application which is really global and distributed. So it is something that you have to have all essential. It is not an optional, right? So partition tolerance is mandatory or kind of requirement for any distributed system. Okay, let's move on to understand some of those pro trade-offs, right? I think we partly touch upon, but I think let's go a little bit more deeper here. So what we are saying is, let's talk about CP systems, right? Consistency and partition tolerance. What we're saying is, it's okay to sacrifice availability a bit. We are saying a bit, not completely, a bit, uh, to maintain data consistency, right? Because application like banking, financial application, anything of inventory, all that health, which are critical, right, for functions, those can't be, or I mean, which is critical to have a similar or not similar, even same data across different nodes. You can't compromise any deviation there. Then you got to have a CP system which are consistent as well as partition tolerance. Different tech that you may use, some of those are like Mongo and others, right? You can use it for a AP system, availability and partition tolerance. What we're saying is that you can sacrifice a bit consistency. Of course, eventually it will be consistent, but you should prioritize availability. That's what we are saying here. So and example could be social media. It's okay to have few seconds delay if you put a post and your subscribers are seeing that, right? But it's not okay that you would withdraw, let's say, 10,000 rupees, and then it take, and you check the status, let's say, and it's not updated and it's still saying the old one. It's not okay. It has to have a quicker turnaround time, right? Quickly you should be able to update all the nodes. So that's where these use cases coming, right? That maybe banking, financial, or where we care about data consistency, you should have a CP systems, and cases when it's okay to compromise a bit of consistency for availability, like e-commerce it could be social media, things like that. You can have AP systems there. Move on. Now let's say some real world example, right? So we talked about banking system, that they should have a CP kind of system or system type. Consistency and partition tolerance should be important. This will really help us to have incorrect, for example, balances. We talked about it. E-commerce, availability is important. If users are coming into your app and your app is not even opening up, it will be, it will not like it, and you may lose customers, right? So it's okay to show data maybe a few seconds later. By the way, folks, we are not talking about an hour later, right? Or even a lot of minutes. It's just about a few seconds. So when we say prioritize, here when we say, let's say for example, somebody saying prioritize consistency over availability, we're not saying that availability will be like several minutes on an hour late. Not really. It is just about a matter of few seconds, right? So it's okay in e-commerce that you are getting confirmation of the order after placing a few seconds later. Nothing magically will happen, but your application is opening is more important, right? If you just are opening, application is not opening, I think that they will be like demoralized than they're seeing their confirmation a few seconds later. So that's when it's about what you prioritize. Social media, of course, AP systems, okay. It's okay that, as I said, it's okay to show up your post in your window a few seconds later, right? Then application is not even opening or it's not responding, right? So that's how, based on the use cases, you prioritize that which one is really important enough for you. Now let's talk about what is PACELC theorems, right? Basically, I would say they have extended it. The base is still cap, but they have added a flavor of latency there. So let's understand what exactly they are saying. Again, after a decade after this, this cap came, PACELC came, and basically they have extended it. They are not saying as a brand new thing, but they have extended to make it more comprehensive algorithm to be specific, right? So they talked about both scenarios. There, while CAP is primarily focused for uh, distributed scenarios, PACELC is covering both scenarios, right? Whether you are a distributor or not. So it's like a comprehensive algorithm, right? So before let's look at the right side, so it will be easy to understand. So we are saying that if there is a network partitioning in your system, if no, means it's not network. I would system application. It's like a maybe bare metal or application which is sitting into some servers, not distributed. Then basically you can have low latency because it's faster, and you can have a consistency. Okay. Uh, and so basically you can choose basically consistency uh, you know here in the you will get more consistency here, and latency will be low because it will be faster because you're on the same, you're not having network partition, right? It will be faster. If you have a network partition, then basically you need to choose between consistency and availability. This is exactly what cap theorem is saying, that in a network partition you need to prioritize either availability or consistency. So left side of it is exactly what I would say cap theorem is saying. Right side they have extended for scenario which is not network partition. So what they're saying is that if application is not having network partition, you have to pick between low latency, means it's faster, or consistency, right? So if you care about too much of consistency, of course it will be a little slower because you got to update in many all kind of data, right, wherever it exists. But if it's okay to have less consistency, then it will be uh, you will prioritize low latency, it will be faster enough. So I think they're covering both kind of scenarios. Okay. uh, so as I said, they have extended that to cover the scenario which is like non-network partition as well. Okay. Now let's talk about different strategies or categories. So we talked about availability and low latencies. I think most common for high throughput when we have low latency and availability at the same time. So you can basically have so here if you look at, you got a 4 different options, right? Uh, you got CA, and again you have L and C on other side, right? So you got a more choice here. So you're saying availability and low latency we're talking about. Again, partitioning will be you will get low latency as well as you have a, I would say, availability as well, right? And for next thing is availability and consistency. So it's like a balanced. So you have mix of both. Uh, in those cases you'll prioritize consistency, and during partitioning issues you will prioritize availability, right? So it's like a trying to have a kind of a combo approach, that which you should be doing in case of mix and match that we talked about here. Now let's talk about some key differences that the traditional cap theorem versus the extended pack ELC theorem is talking about. So I think I just said that focus is primarily for network in cap, and in pack ELC they have talked about both normal operation as well as partitioning scenarios. Trade-off, of course, you got to choose between C and A, and here you can have C versus A, means you can pick one, and from there you can have L versus C. So normal operations and partitioning options both are covered, right? Uh, Again, it is for all and it is for failures. Latency is considered in the pack ELC is important. And again, you have got a more categories, right? Nuance, like which you can pick and choose. So again, it includes latency as a factor, and latency is important, folks, right? In distributed system as well, it's one of the critical criteria for any system. If there is too much latency, then of course users it will be like losing the users, right? So it's like a more nuance. Uh, but yeah, fundamental for partitioning is still CAP, right? So CAP covers primarily network scenarios or network failures scenarios. Okay, some of the practical guidelines about when designing this system. So, for example, financial system. So, of course, uh, you should have this kind of partition tolerance consistency, or basically consistency, I would say, systems, right? You can't afford consistency should be there in all the time, right? For these applications. For social media, you will prioritize availability. Okay. So availability is important here. uh, and for e-commerce, of course, you will have a balance of availability and consistency. You can't go completely, you can't ignore consistency. I would say it matters more in e-commerce than social media, because there is some financial angle as well in e-commerce, right? You got to pay as well, unlike social media, where it's mostly about chatting and collaboration. So that's where there's a balance of, I would say, availability and consistency in case of e-commerce. Here, financial, of course, consistency is important in all the cases, and in case of social media, primarily look for availability. Okay, so these were the I would say considered. Now, just to summarize the takeaways, so we talked about CAP theorem, where you got to choose between consistency and availability during network partitions, you know uh, and in pack ELC theorems, we're talking about that, where you can manage with latency versus consistency, right? So you can choose between consistency, where we have a little bit more latency, versus latency, where of course it is faster, right? So you got to pick those cases, and it's for all the conditions, right? Not just for failures. Okay, so again, I would say we're done. Thanks for your time, and yeah, and we'll come back again to cover other aspects of system design. Okay, so take care. We'll talk later. Thank you.